All right. Okay, so let me first begin by thanking the organizers for putting this conference, this meeting. So finally, we are back in business. So it's wonderful to be back here and seeing all the old friends. Okay, so let me begin. So I'm going to talk about some of the works that we have been doing for last couple of years, looking at bounds on fluctuations in context of thermal machines and its connection with the so-called thermodynamic uncertainty relations. This work is done in collaboration with my PhD student Sushant, who is also going to talk about something completely different in this session, and with Sandeepan and Divira Segal from University of Toronto. So I'll be highlighting some of the main results, but the details you can find in the set of 3 papers that are given here. Okay, so a brief outline. So I'm going to give you a background about why we are looking at fluctuations and what is so-called TUR, the thermodynamic uncertainty relations. And then I'll talk about this bound on fluctuations in the context of 2 type of thermal machines that are quite popular. One is so-called continuous thermal machine, and another is a particular type of discrete machine, so-called auto engine. Okay, so let me begin with a brief motivation. Why fluctuations are important or interesting? First of all, we all know that fluctuations are not arbitrary. In equilibrium systems, we have the very famous fluctuation dissipation relation, which provides a lot of interesting information. For non-equilibrium systems, and by non-equilibrium, what I mean for this talk, at least, imagine you have certain, some kind of a system which is coupled with at least, let's say, 2 reservoirs, which are at different temperatures or different chemical potentials, and therefore there are currents that are flowing in the system, and you are, let's say, in a steady state. So there is a so that's a class of non-equilibrium system, and in those systems we have understood now fluctuations in terms of the so-called universal fluctuation relations like Galotti-Cohen type. Uh, what more do we know? So now in recent times, in terms of these fluctuations, there is a very interesting relation that has been given, known as thermodynamic uncertainty relation. It's actually a relation which involves, which is actually a precision cost relation. What does it mean? Look at in this kind of system, any particular current, which is, let's say, J alpha, and its variance, so this is second order, the C refers to cumulant. So this is nothing but like a noise to signal ratio or a precision of your current. And the point is that you can't arbitrarily make this noise to signal ratio to be arbitrarily precise. You have to pay a cost, and that cost is related to the entropy production rate of the system. So there is this bound that was given by Udo Seifert initially, and turns out to be valid for a large class of systems, particularly in systems in linear response. And beyond linear response, for Markovian dynamics, you can show it to be true. And it's true for arbitrary set of currents that you can have in your system. Now, the question is that why this is interesting. There are multiple reasons. First of all, you can actually infer entropy production, which is typically difficult to infer, by measuring any one particular current and at least try to get some inference that what is the entropy production. The other very interesting thing that happens because of this, if you have, let's say, 2 currents flowing in the system, you can think of constructing an engine, and you can talk about efficiency and fluctuations of various quantities. Now, what happens just because of this bound, a very interesting bound on efficiency was given by Udo and Patrick, which is of this form. And this bound turns out to be tighter than the Carnot, which we know from second law. Our traditional second law of thermodynamics gives us this bound. But now, as a consequence, you bring fluctuation in your theory, and you get a new bound which is tighter than Carnot. And what it tells you is that you cannot reach Carnot bound at a finite power output until and unless you have diverging power fluctuations. So there is a trade-off between power efficiency and power fluctuations. So you cannot construct an engine which have a finite power output operating at Carnot efficiency and have a reasonable power fluctuation. So that is not possible. Okay, so this is sort of interesting sort of results that were found in the, in recent times. But what we were interested, what did we ask? So we asked the basically following question, that if we have this kind of setup with 2 affinities, meaning temperature difference and chemical potential difference, let's say, so you can talk about 2 currents, let's say charge current, let's say electrons, it's an electron system, so you have, let's say, charge current and heat current or energy current. So I can write TUR for individual these 2 currents. Now the question is that are they independent? Are these 2 relations, one for written for charge current, another written for energy current, are they independent? The answer turned out to be no. They are not independent, but in certain context. And the context is that if I consider this kind of, so this is I'm calling continuous thermal machine, meaning this is always in contact with a bath. The system is always in contact with a bath is what we call as continuous machine. Now, given this kind of setup, the thermodynamic uncertainty relation for different currents are not independent. They are connected, there is a hierarchy, but not in arbitrary regime, but in regimes when this kind of setup work as a machine. Okay. What does it mean? So for example, this setup, I can think of a thermoelectric engine. I can operate it as a thermoelectric engine or a refrigerator, meaning I can just use the heat current from the hot bath and channelize the particle or electric current against the chemical bias, right? So that would be my thermoelectric device. And given this device, if I now look at the two currents, particle current and the energy current, the TUR will not be independent. And that one can actually show in the linear response to be valid. So in the linear response, of course, these two currents, this is a particle current and the heat current, you always have this kind of expansion in terms of the affinities, the delta mu and delta T, and these are Onsager coefficients, and they have very nice relations among themselves. So given this setup, of course, you have this work current and heat current, right, which can be easily found. Now, the central result is that whenever you are in the linear response regime and the setup is working as a useful device, meaning let's say engine or refrigerator, you always have a hierarchy between the TURs. And how does the hierarchy? The hierarchy is that the output current, if you're looking at an engine, let's say, you have work output and heat input. Your output is always larger than input. Okay, so there is a strict hierarchy that you get, but only when your setup is a useful device. And this proof simply follows from the Onsager's relation and the positive semi-definite property of the Onsager matrix. Once you have those, you can very easily prove that if you get rid of sigma from both sides, because sigma is positive, entropy production rate has to be positive, you also can immediately see that the fluctuation or relative fluctuation of work output is always greater than relative fluctuation of input heat. So this also tells you that you can't win. You want a machine where you want to get a reasonably small fluctuation in output, but that's always going to be larger than input. And another remarkable result that you, as a consequence of this, you immediately start getting another very interesting sort of a bound where we construct this quantity called eta 2, which is nothing but the ratio of fluctuation of output current divided by fluctuation of input current. Turns out this gets both lower and upper bound. This eta 2 gets lower bounded by eta average square and upper bounded by eta c square. So this is like one order higher information of our traditional efficiency. And as a consequence, you now get a very interesting bound.
2 plus 2 minutes left.
Okay, 2 and 2, right? Okay. So a very interesting bound, which is that average efficiency gets now a tighter bound than Carnot. So our standard thermodynamics teaches us that average efficiency is bounded by eta c. But once you bring fluctuations into account, you start getting tighter and tighter bounds. And this is, I just showed it for engine, but of course it's also valid for refrigerators. So this is just some numerical results. So of course for free fermions, you can actually very simply calculate currents and fluctuations. There is a standard Levitov-Lesovich formula for that. So you can use that and you can try to see what happens. So this is a plot which shows that the lower bound is valid. Eta 2 is greater than eta average square. And this plot is with respect to this gamma, which is system bath coupling and dot energy. So this is for a single dot coupled to two reservoirs. And you have this bound to be valid as well as upper bound to be valid. So this is in the linear response. We also observed that this bound is valid beyond linear response, for which we don't have a proof yet. But it turns out that this has a validity beyond linear response. So we have also generalized this in other contexts. For example, now if you break time reversal symmetry, then of course Onsager relations modifies a bit. You get Onsager-Casimir relation. And turns out that these bounds, particularly the upper bound, stays robust, and lower bound you have to modify a bit. And also in the context of non-autonomous engine also we have done some generalization of this. But I'll just end with a couple of one point about mentioning about the finite time engine. So there is this class of, so we ask what, so this was results for continuous thermal machines, but you can also ask what happens if you have discrete engines, meaning when the engine's operating not always in contact with a bath, but there are, let's say, thermalization strokes, but also unitary strokes when the system is not coupled to bath. Does these bounds immediately translate? The answer is no. it doesn't. But let me just highlight that. So even in this kind of auto cycle, you can once again look at the work and heat and their fluctuations. So I'll just take 1 minute. So we saw that if you just take a two-level system and run a cycle, the auto cycle, it turns out this bound is again respected. That eta 2 is greater than eta average square and is always positive. So that is true. Here U represents this non-add. So you take a two-level system and when you are driving it, this U captures the how fast you are driving. But no matter what, this bound is valid. So again, relative uncertainty of output is greater than input. We also did a very simple exercise with the harmonic oscillator and realizer engine, a parametrically driven harmonic oscillator, and once again we find this to be true. But what about the general? The answer is, so recently we are trying to work a general statement we're trying to make, because so far these were the two toy models. So we try to construct the linear response theory for auto cycle, and turns out that you can actually show that the lower bound is always valid, but there is a hint that the upper bound may not be respected. And in fact, that is now what we also find, that the upper bound is getting violated, but there is a new bound which is less than 1. So I just want to finish with the statement that the nature of the average efficiency, no matter whether you take continuous engine or discrete engine, is always bounded by eta c. When you look at fluctuation, they kind of becomes different. The reason being you have a continuous engine where the setup is always working, always in contact with the bath, whereas for discrete engine is not always in contact with the bath. So nature of fluctuation differs at that level and gives you different bounds. So that's kind of with which I want to finish, and this is the take-home message, and I want to thank also the grant agency for funding. Thank you.
Now we are open for questions.
No, so this TUR, I mean, has it been proved for like quantum systems? I mean, is there a
Okay, so not for in certain regimes, yes. It has been shown that for the quantum systems, it can go below 2, and it can be 1. So the right-hand side turns out to be can be 1. So that is the new bound for quantum system. But if your system is always in the linear response, you can show it to be always greater than 2, because that follows from Onsager, and Onsager is always valid.
But actually, it's a lower.
But if you go beyond the linear response, you can actually show quantum system offers a lower bound, which is 1. But that is also slightly restrictive. I mean, not fully, doesn't work in all entire regime, but in some limit. But it can go below. Just like even the classical system, non-Markovian dynamics also can, there is a violation, it can go below.
So for what cases does eta c squared saturate the bound?
Okay. So this exactly when, just like the average efficiency saturated to eta c, zero entropy production. So when you're like
what kind of distributions of the current do you have in that case? Is it Gaussian? No.
Distribution of current need not to. That's a interesting point. What would be the distribution of current? It's a zero entropy production.
But zero entropy production saturates. Okay, thanks.
Yeah, so that certainly saturates this bound.
Thank you.
Okay, let's thanks to the speaker.